My name is Xiaoming Zhang from City University of Hong Kong. Thank you for watching my video. Today I will first give an introduction on reinforcement learning and then introduce our recent work about the comparative study on state preparation with reinforcement learning and traditional algorithms. To begin with, reinforcement learning, we should usually consider a so-called Markov decision process. We may consider an artificial agent with its state S, action A, and reward R with different value of S. And our goal is to optimize its policy, or the probability of choosing each action at each state, in order to maximize the total reward we can obtain. In quantum optimal control task for state preparation, we may define the state as quantum state, and the action as Hamiltonian, and the reward may as a function of the fidelities. To perform optimization, we define an action value function, which describes the total reward one can obtain in the entire optimization process. Here gamma is the reward decay rate, which is larger than 0 and smaller than 1. The corresponding policy is that at each state S, we just choose the Q value, the action with highest Q value. So our goal is to optimize the value of Q for all states. And actually it can be observed that for optimal policy with maximal Q, the Bellman equation is satisfied. So we should minimize the difference between left-hand side and right-hand side of this equation. The simplest reinforcement learning algorithm is the tabular Q-learning. So for example, we are currently at state S5. The largest Q value for it corresponds to S3. So we take the action 3, which drives the state to S2. And this process goes on while the Q table is updated according to certain rule. One of the problem of the tabular Q-learning is that it can only store the Q value of limited number of states and actions. For high-dimensional problems, it is impossible to write down all the states. But this problem can be solved by the so-called deep Q-learning, where the Q table is replaced by a neural network. The states can be represented by a high-dimensional vector, which serves as the input of the network. The output of the network is just the Q value for different actions. Here. And all the input states and output Q value are stored for the neural network training. The deep Q-learning algorithm is capable to deal with much more complicated problems, actually. And we also consider two traditional algorithms, the stochastic gradient descent and the Krotov method, for our comparison. To discuss how these algorithms are different from each other, we first consider a simple task of single-qubit state preparation. The state is initialized at 0, and our goal is to drive it to state 1, with the Hamiltonian as follows. And we set the operation time to be t equals 2 pi, which is divided into totally n pieces. It can be observed that the RL reinforcement learning algorithms generally perform better for small n. Because have a small n, the agent is much easier to find the target states with much less required steps. As n increases, it takes more steps to reach the target, so its performance drops. We also trace the path shape and state trajectory in the block sphere. Actually, the reinforcement learning can find the simplest control schemes. This is because the reinforcement learning can terminate the game whenever the target state is reached during its exploration. In other words, it can adaptively change the number of segments. However, the traditional algorithms should always fully use all the n steps, which may result in a much more complicated control schemes. Actually, because of reinforcement learning can not only find the target state but also adaptively change the number of segments, it's suitable to be used to explore the quantum speed limits, the fastest control schemes. And we have provided an example in our previous work here. We also extend our discussion to the multi-qubit case. We have considered a quantum state transfer problem in spin chain with fixed coupling strength and tunable external magnetic field. And the magnetic field is initialized randomly. The task is to transfer an excitation on one side to another. The results show that the reinforcement learning have better performance as the number of spin increase. This indicates that the reinforcement learning algorithms can actually deal with high-dimensional problems. The comparison is summed up at this table. So we have just discussed 3 parts of it, and we haven't introduced the algorithm of policy gradients, PG. So for more information, you may find our recent work. Actually, the reinforcement learning can have other advantage over the traditional algorithms. The first one is the generalizability, which means that the policy optimized in one task can actually be used in another similar task. And we are also studying the universality of reinforcement learning. It means that a single agent can actually deal with multiple tasks. For example, in state preparation, it may capable to deal with the state preparation with the reinforcement learning can deal with state preparation with multiple target states and initial states. Okay, with this, I would like to thank you for your attention.